Mars just kind of turns into a hazy red ball, and we can't see surface features anymore with our satellites. The dust, it's not like sand, it's like talcum powder. It's very, very microscopically small, nasty dust particles.
Delving into Martian landscapes might deceive with a calm facade, but the intrigue deepens as the curtain lifts on colossal dust storms, a breathtaking phenomenon in the Martian theater. These superstorms, emerging every 3 Martian years, wield the power to cloak the entire planet, plunging it into darkness for weeks or even months, challenging the resilience of technology. The quest to establish humanity on Mars encounters riveting hurdles, wrapped in the enigma of our limited comprehension of these celestial storms. Step into the extraordinary as we embark on a captivating journey through the universe, unraveling the captivating mysteries of Martian superdust storms. This is Reveal the Mystery. If you are curious to learn mysteries of the world, space, and beyond, consider subscribing. Mars didn't always contend with massive dust storms. In its earlier epochs, Mars featured a thriving environment characterized by a dense, warm atmosphere supportive of flowing water. However, across billions of years, Mars underwent a desiccation process, causing its atmosphere to gradually diminish to less than 1% of Earth's atmospheric volume. The emergence of these dust storms cannot be solely attributed to Mars turning arid. Although the precise origins of these storms remain partially enigmatic, the prevailing notion is that Mars' temperature plays a pivotal role. Despite elevated CO2 levels, the reduced atmosphere made Mars less adept at retaining heat. With an inadequate ability to trap warmth, the planet's surface cools swiftly, leading to significant temperature disparities. For instance, standing at the planet's equator during its warmest phase might result in a foot temperature of 28 degrees, while the head registers 0 degrees Celsius. Consequently, Mars undergoes pronounced temperature fluctuations, ranging from daytime highs of approximately 27 degrees C to nighttime lows plunging to a frigid 133 degrees C. These temperature variations instigate the formation of winds, which, in turn, propel diverse weather systems across the planet. Unlike Earth, where weather is shaped by rain and water cycles, Mars now experiences weather patterns dictated by cycles of dust. Remarkably, dust assumes a pivotal role on Mars, and without it, the colossal planet-spanning storms would likely never manifest. Although the Martian atmosphere is too thin to efficiently capture and transport heat, the presence of Martian dust proves transformative in this context. The commencement of this process hinges on Martian dust entering the air, facilitated by various mechanisms. One notable mechanism involves the occurrence of dust devils, with Mars witnessing thousands annually, particularly during the Martian spring and summer, causing adjacent air to rise and drawing cool air from the atmosphere to fill the void. These opposing winds generate spirals of rising air, attaining dimensions of hundreds of meters in width and 8.5 kilometers in height, albeit many are smaller. As these spirals traverse Mars' expansive deserts, they draw in and propel dust into the atmosphere, resulting in a lingering dust haze in Mars' atmosphere. While dust devils offer a visually striking method of introducing dust into the atmosphere, they are not the predominant means of this occurrence. Much more prevalent is the straightforward impact of wind traversing the dusty surface of Mars, a phenomenon known as saltation. The dust on Mars proves surprisingly resistant to becoming airborne. Small particles exhibit substantial cohesion due to a slight electrostatic charge, akin to packing peanuts, causing them to adhere together. Consequently, these particles require a certain amount of momentum to initiate their movement. Interestingly, larger particles, experiencing less cohesion, are more easily set in motion by the wind. Gusts of wind lift these larger sand grains, moving those short distances. However, due to their ultimate heaviness, they eventually descend. The force generated by these impacts imparts enough momentum to overcome cohesion and elevate the lighter dust into the air. Once airborne, Mars lower gravity facilitates the prolonged suspension of dust in the atmosphere, lasting for weeks or even months. This extended presence initiates the formation of storms because, in contrast to the sparse air around them, dust particles efficiently collect heat from the sun. As the sun warms the dust, it acts as miniature radiators, gradually releasing accumulated heat into the surrounding air previously transmitted to the ground below. This warming effect expands on a grander scale than the formation of dust devils earlier. The rising air mass draws in wind from the sides, intensifying the process. Increased wind results in more saltation, more dust propelled into the atmosphere, and a greater opportunity for atmospheric warming. Eventually, this uncontrolled sequence culminates in a regional dust storm. Fortunately, on a local scale, a dust storm on Mars poses minimal danger. Wind speeds peak at 97 km/h, only half the velocity of hurricane winds on Earth. Furthermore, due to the thinness of the atmosphere, the sensation is minimal even when the wind is moving swiftly, comparable to an individual having less pushing power than a crowd. Despite some depictions in science fiction stories set on Mars, dust storms lack the force to topple spacecraft or damage satellite dishes. Nevertheless, these storms bring their own set of risks. For instance, a Martian rover relying on solar power faces significant challenges if a dust storm laden with slightly sticky electrostatic particles passes overhead. Over time, dust deposition from such storms can sufficiently block sunlight, preventing it from reaching the rover's solar panels, leading to the termination of more than one Earth-based mission. The complications escalate when these storms grow in size. Mars follows an elliptical orbit rather than a perfectly circular one. Annually, during the Martian southern hemisphere's spring and summer, the planet reaches its closest proximity to the sun, experiencing its peak warmth. During this period, regional dust storms in the southern hemisphere have a tendency to amalgamate into a superstorm of continental proportions. While it's plausible that these storms coincidentally form in close proximity, their consistent recurrence each year suggests a more intricate explanation linked to rising temperatures. The continent-sized storms are only one level of the phenomenon, and scientists currently lack a comprehensive explanation for the next stage, the planet-sized storms. These colossal storms occur approximately every 3 Martian years, a relatively short timescale that rules out Milankovitch cycles, which typically operate on scales ranging from thousands to hundreds of thousands of years. The possibility arises that some aspect of the dust cycle requires a replenishment period, taking about 3 Martian years, or roughly 5.5 Earth years, although the specifics remain uncertain. While most dust storms on Mars endure only a few days, these apex storms can persist for weeks, significantly impacting any human technology in their vicinity. Scientists gauge the sunlight availability on Mars using aerosol optical depth, AOD, which measures how much sunlight is absorbed or reflected by airborne pollutants. Mars typically maintains an AOD of around 0.5. For context, an AOD of less than 2 is necessary for rovers like Opportunity or landers like InSight to charge their onboard batteries. In comparison, the AOD of thick smoke from a wildfire on Earth, which turns day into night, reaches 7. However, the planet-sized dust storms on Mars reach AOD levels of 9 to 11, representing nearly complete light blockage. In 2018, such a storm led to the demise of the Opportunity rover by overwhelming its solar panels, pushing it into hibernation mode. The lack of power in the onboard heaters, coupled with fluctuating day-night temperatures, caused irreparable damage to the rover. These storms pose challenges not only for solar-powered rovers like Opportunity, but also for those equipped with nuclear batteries, such as Curiosity. The dense clouds obstruct communication to and from the Martian surface, compelling scientists to wait out the storms. Even satellites are not immune, as the substantial amounts of warming dust in the air cause the entire atmosphere to expand, encroaching into the orbital paths of satellites. To prevent an unplanned descent from the Martian sky due to atmospheric drag, Satellites must expend precious fuel for course corrections. Settling on Mars poses imperative challenges for humans, requiring solutions to overcome reliance on solar power during storms, potential freezing threats, and the risk of isolation due to satellite communication loss. Mars settlers must be highly self-sufficient, as mishaps during storms could hinder calls for assistance. Despite their initial impact, these storms prove self-destructive over time, as substantial light blockage leads to insufficient surface warming, diminishing the essential upswelling winds. The storms deplete their resources and gradually dissipate, restoring tranquility to Mars. In 2023, NASA's Curiosity and Perseverance, along with China's Zhurong, remain active. Zhurong, the only solar-powered rover, faces cautionary measures after the 2018 superstorm. Given the approximate 5.5-year cycle, the next storm may be imminent, with a gentle breeze signaling its potential recommencement.